Welcome to this video where we dive into an intriguing cosmological problem. Let's start with the problem statement. The first Friedmann equation can be expressed as the square of the time derivative of the scale factor divided by the scale factor squared plus the curvature term divided by the scale factor squared equals 8 pi g over 3 times the energy density. This equation can also be rearranged as 1 minus omega equals negative curvature term divided by the scale factor squared, where omega is defined as the energy density divided by the critical density. Now, let's assume that the curvature term is small when compared to the energy density, which predominantly consists of the cosmological constant. This scenario leads to an inflationary universe. Our task is to show that the longer this inflationary period stretches out, the closer omega gets to 1. In part B, we need to break down the flatness problem in words and elaborate on how it is resolved by inflation. This problem is fascinating because it touches on fundamental questions about the universe's structure and evolution. By exploring the Friedmann equation and the concept of inflation, we gain insight into why the universe appears so flat and uniform on large scales. Understanding these principles not only enhances our knowledge of cosmology, but also helps us appreciate the fine-tuned balance of forces that govern our universe. We start with the first Friedmann equation. The square of the Hubble parameter, which is the rate of expansion of the universe, divided by the scale factor squared plus the curvature term, which is k over the scale factor squared, equals 8 pi g over 3 times the energy density, ρ. Next, we can rewrite this equation by factoring out the energy density, ρ. The square of the Hubble parameter divided by the energy density, ρ, plus the curvature term, k, divided by the scale factor squared and the energy density, ρ equals 8 pi g over 3. Now, considering that k is much smaller than the energy density, we can say that the ratio of k to ρ is much less than 1. This allows us to simplify the equation by neglecting the k over ρ term. The square of the Hubble parameter divided by the energy density, ρ equals 8 pi g over 3. Therefore, we can write the following simplification. Since k is much smaller than ρ, the ratio of k to ρ is much less than 1. One can consider that the square of the Hubble parameter divided by the energy density, ρ, equals 8 pi g over 3. This simplification is key to understanding how the equation behaves under the assumption that the curvature term, k over the scale factor squared, is very small compared to the energy density, ρ. By making this approximation, we can focus on the primary components that drive the dynamics of the universe's expansion. Let's continue with the next part of our solution. Since the energy density, ρ, is mostly the cosmological constant, ρ lambda, we can approximate ρ as being equal to ρ lambda. The equation then becomes the square of the time derivative of the scale factor equals 8 pi g over 3 times ρ lambda multiplied by the scale factor squared. Taking the square root of both sides, we get the time derivative of the scale factor equals the square root of 8 pi g over 3 times ρ lambda multiplied by the scale factor. The derivative of the scale factor with respect to time equals the square root of 8 pi g over 3 times ρ lambda multiplied by the scale factor. And with a little bit of algebra, we get the equation below. The derivative of the scale factor with respect to time minus the square root of 8 pi g over 3 times ρ lambda multiplied by the scale factor equals 0. Let's call dA over dt as d, the differential operator. The equation then becomes d minus the square root of 8 pi g over 3 times ρ lambda multiplied by the scale factor equals 0. With a little bit of algebra, we get d minus the square root of 8 pi g over 3 times ρ lambda multiplied by the scale factor equals 0. Now there are several ways to solve this differential equation. In this case, I wrote it in a way that resembles the differential operator method, but in reality, the solution is very straightforward. The scale factor a of t equals k times e raised to the power of the square root of 8 pi g over 3 times ρ lambda multiplied by t. Now, for a long scenario, for instance, such that t approaches infinity, we would have a of t approaches infinity, but also the time derivative of the scale factor a of t approaches infinity. Since the time derivative of the scale factor a of t equals k times the square root of 8 pi g over 3 times ρ lambda multiplied by e raised to the power of the square root of 8 pi g over 3 times ρ lambda multiplied by t. Therefore, when we substitute into the equation for 1 minus omega, we get 1 minus omega equals negative k over a squared, which we approximate to 0. This tells us that 1 minus omega is approximately 0, which leads us to conclude that omega is very close to 1. This result is significant because it suggests that the universe is nearly flat, with omega being almost equal to 1. The concept of a flat universe is crucial in cosmology as it aligns with observations and theoretical models that describe the large-scale structure and evolution of the cosmos. A universe with omega close to 1 implies a delicate balance in the initial conditions of the universe, supporting the idea of inflation as a mechanism that drove the universe towards flatness. Of course, when applying the limits we just mentioned. Let's move on to the second part of the problem. Part B. Today, we observe a universe with a curvature that is very close to 0. This observed flatness of the universe presents a significant problem known as the flatness problem. Without the mechanism of inflation, the universe would require an extremely precise and fine-tuned initial condition to maintain such a state of flatness over time. The flatness problem arises because any slight deviation from perfect flatness in the early universe would be exponentially amplified over time. In a non-inflationary scenario, if the universe had even a small positive or negative curvature, this curvature would grow rapidly, leading to a highly curved universe that we do not observe. Inflation theory provides a compelling solution to this problem. During the inflationary epoch, the universe underwent an extremely rapid exponential expansion. This expansion effectively stretched the fabric of spacetime, driving the geometry of the universe towards flatness. In summary, the flatness problem highlights the difficulty in maintaining a flat universe without fine-tuning initial conditions. Inflation provides a natural mechanism that explains why the universe appears flat today. By exponentially expanding the universe, inflation drives the geometry towards flatness, solving the flatness problem without the need for fine-tuned initial conditions. This problem is fascinating because it touches on fundamental questions about the universe's structure and evolution. By exploring the Friedmann Equation and the concept of inflation, we gain insight into why the universe appears so flat and uniform on large scales. Understanding these principles not only enhances our knowledge of cosmology, but also helps us appreciate the fine-tuned balance of forces that govern our universe.